Yeah. So very much welcome to the lecture on Action and Cognition. Today I would like to start shortly to discuss a few books which you might use for reading up the stuff. There is, I don't think, a perfect book for the stuff we are doing here, because in the books you read what we know, and if you have titles like Cognitive Science from Molecules to Mind, you will find that there is a lot about molecules, transmitters, receptors, cells, and so on. And the stuff about how cognition works is limited in scope, because we don't know that much there. So I selected a few books which are best suited. One is Neuroscience by Baer et al. And it's a very nice book and has the advantage there's a German translation available of the same high quality. So these two books I like a lot. There is a Kandel. Kandel is the foundation, so everything is in there, of course. It is not a book which you can read from front to back. It's just way too much. But if you want to look up certain stuff, then Kandel is certainly a top reference. So this is very high quality. In principle, it is slightly dry to read, but it's very good. And there's by Doodle Neurowissenschaft, a German book, which is a more recent date and also a very nice one. So these are my recommendations. If you come up with other books which you like a lot, please point them out to me. I would love to have a look, and we might discuss it here as well. Next is questions. So you remember last lecture where we were discussing ventral and dorsal pathway. And question 1 goes pretty much to the heart. Explain the major division of the visual system into a ventral and a dorsal pathway. What is the experimental evidence? So I would consider this a medium level question, maybe a difficult question, depending on how detailed we go into here. So, and I like to start with the principle. What is the stuff with the ventral and dorsal pathway? Who would like to make a statement? Yes, please.
Well, from V1 on, the processing of visual stimuli is, so to speak, split up, or from V2 higher, into analysis of coarse structures and motion, which is done in the dorsal pathway in the parietal cortex, and the more fine-grained analysis of structure and shape, which is done in the ventral pathway, which is mostly in the temporal.
Mm-hmm. Okay, can you give two catchwords for the two pathways?
The where is where pathway and the what pathway, or the where or how pathway is the dorsal one and the what pathway is the ventral one.
Wonderful, thank you. So just I repeat it for the microphone. There's a division, and you emphasize correctly, from primary visual cortex on into a dorsal pathway, also called where or how, relating to processing of spatial relations, and a ventral pathway related to processing of object identity, also called what pathway. The division, or let's say the statement from V1 on, is important because we have dealt with the parvo- and magnocellular division, which originates in two different types of ganglion cells in the retina, is maintained in the LGN with the different layers, 1 and 2 for the magnocellular pathway, giving the name because the cells there are large, and layers 3 to 6 for the parvocellular part, being the main afferents to primary visual cortex. And if you have two channels input, two channels output, it's a natural question to ask, okay, is there a one-to-one match? And no, it's more complex. There is a certain mixture, and the classical ventral dorsal pathway relates to the cortical part. What is the experimental evidence? So here I'm asking for the classical experiment done in monkeys with a lesion study. Who would like to describe such an experiment? Take you, please.
Yeah, so when the monkey had a lesion in the parietal cortex, which is part of the dorsal pathway, it had problems determining the position of an object in a landmark task, for example, but it can still determine the shape or the color, so the typical other properties of the object. In contrast, when there was a lesion in the temporal cortex, which is part of the ventral pathway, the monkey cannot determine the shape of the object anymore, but he can still determine its position.
Yeah, okay, thanks a lot. This is importantly a double dissociation. So he nicely emphasized that if you have one lesion, the monkey can do one task still, but the other one not anymore, and vice versa with the other lesion. So it is not a general deficit. So if you lesion an animal large enough, of course it cannot do a whole variety of tasks, but this would not prove functional specificity. And with a double dissociation, if you have the lesion in the ventral pathway, you have problems with object identification or memory thereof. And if you have a lesion in the dorsal pathway, you have problems with a landmark task. This is a catchphrase how I remember it as well. But when I ask you, for example, to detail the experiment, and with these questions in the exam, sometimes I add, okay, please describe the experimental setup and procedure in detail, then I would like to hear all the details. And of course, saying the monkey does not remember objects anymore is not good enough. And also be clear to yourself which evidence would convince you. So last lecture, we had that there are different objects. So I had the colorful caps of my pencils here. And I place them here. And then there's a curtain drawn. So this is an important detail for the experiment, that you take away the knowledge of the monkey. So for example, if I put a raisin below the red cap, of course the monkey can fixate the place where the raisin was, and this has nothing to do with object identification. It's important that the experiment is slightly more complex, showing two objects, drawing a curtain, so the monkey must memorize both objects. In the meantime, I switch the object somehow and put the raisin not below the new object, but below the one which was shown before as well. So the monkey must memorize the identities of the previously shown objects. This would be the delayed match to sample task. There are variations, delayed non-match to sample, and so on. So there are different ways you can hide the raisin. But you must construct it in a way that for the monkey it's essential that he cannot cheat by just staring to one location and not really caring about the objects. Okay. What is the order of magnitude of response latency in primary visual cortex? So here a number is asked for. A number and a unit. So who would like to make a go? Is it days, weeks? No, I'm joking. So you have a guess. I flash on a visual stimulus. How long do I have to wait till in your primary visual cortex there's some activity? Ballpark. Milliseconds is already a very good unit. So now we need a number. Yes, please. 50 milliseconds is perfect. Yes. I would be very happy with such an order of magnitude, 50 milliseconds. The parvocellular part is a little bit slower. The magnocellular part is a little bit faster. 50 milliseconds is just a very nice answer here. Give an example of the non-classical receptive field effect. What is meant here? Border ownership was one example. There are many more examples. Or can you explain what a classical receptive field is before we go to the non-classical receptive field? Yes, please.
It's a dark bar on a light ground or a light bar on a dark ground, maybe?
This is a stimulus you put onto the receptive field, so to say. The receptive field is a virtual construct, a property of the neuron. So rephrase your answer that you are saying something about the neuron.
It's neurons that answer to dark bars on light ground.
Yeah. So, the receptive field is a region in space where you have to place, for example, dark and light bars to induce activity in the neuron. So I could phrase it, if you put the visual stimulus onto the receptive field, it's a necessary condition to induce activity in the neuron. Okay? And no stimulus in the receptive field, no activity. So around you can do whatever you want, the neuron won't be impressed. Yes, please.
Just a question, is it because it's classical, then we should say it's the concentric receptive field?
So the classical receptive field of neurons in the lateral geniculate nucleus are actually centers around circular and have this property. The classic receptive field of other neurons might be different. So it's a special property of the LGN neurons. The non-classical receptive field is now a part beyond the classical receptive field, which still influences the neuronal activity. Yes, please.
Isn't the main point there that we actually have this global view, like we had with the borders, that then we have a global view and can actually see the whole picture in a way of the object, and then recognizing which object actually has the borders?
This was a beautiful example, but it's an example. Not all non-classical receptive field properties have to be of that type. So what she mentioned is, we had the example that we have a bright, dark contour on the receptive field, so we have activity of the neuron. This is a necessary precondition that we can modulate it, because a non-classical part of the stimulus by itself would not induce any activity. Now we can play a game. We have the same local contrast, but we make it part of a rectangle which is to the left, a contrast inverted rectangle which is to the right, or large or small. We change the contrast of the background and foreground, so we can play around. And this is an example of a non-classical receptive field effect because it had a large influence on the activity of the neuron, whereas locally it was always optimally stimulated. So non-classical receptive field effects are effects of visual stimuli. You could make the same argument in auditory cortex. So effects of stimuli which by themselves not induce activity but modulate activity. Okay? Which means they are naturally highly nonlinear, because by themselves they don't do anything. They must multiply or divide the activity induced by other properties. And they can be extremely complex. Let's say you have the optimal stimulus of a vertical bar. Some neurons respond better if you do an orthogonal bar on top or below. They might respond better or worse if you do parallel bars to the side. And you can do a whole universe of stimuli. These non-classical receptive field properties are pretty important for further processing, but very complex. I also had this nice diagram prepared. Okay, so far so good. I will start today's new stuff with a somewhat softer part, the Gestalt psychology. And you already mentioned you are seeing the whole and the global stuff. This relates here. So when I ask you to describe what is visible here, one valid answer would be 3 Pac-Men facing each other. That's okay. That's what it is. Other people say, well, there are 3 black discs and a white triangle superimposed. And it's a valid answer, because it would look exactly this way. So this drives home the point that vision is ambiguous. There is not a one-to-one match of the visual input to the physical reality, if it exists, to us. The 2 answers are both valid, and we must think about, okay, why do people come up with such explanations? So, for example, if I ask you what is visible here, actually most people would say, well, it's a white sphere with black spikes on it. The alternative answer of a strange 2D silhouette or so is rather uncommon. So you take a two-dimensional stimulus and you interpret it as a real whole gestalt which would give rise to such an input. Or if I ask you what's visible here, well, this is a strange painting, but some people would say it's Nessie, monster in Loch Ness. So you see here the surface of the lake, and here's the head, and she's like a serpentine poking out of the water. So you explain the visual impression here with one global gestalt. And this was pretty much the rage, early 20th century, connected to people like Wertheimer, Köhler, and Kafka. And there was always an up and down, and with behaviorism and all that stuff. I would like shortly to explain the principles they come up with. Wopsa. So when I ask you here what is visible here, and you say there's a white triangle, partly covering the black disk, then you probably say, okay, this is the easiest, most meaningful interpretation. And you would like to have some concepts. And so, for example, here's a list of concepts I come up with. Law of proximity, close stimuli will be grouped. So, for example, you would group these two circles each to one, and this setup is then repeated. Similarity would mean that you group these two circles, these two squares, these circles. Also the distance, the proximity does not play a role here. So the distance from that circle to the square or that circle is identical. Law of common fate, what moves together belongs together. Maybe the strongest Gestalt law. This cartoon should indicate the common movement of all the circles, meaning that they belong to one and the same object, might be the texture on a certain object. Interpreting such lines, we would probably say these are two lines crossing, whereas here with a minor change, this is obviously two peaks opposing each other. So it's a law of good continuation in a sense. This line being extended, crossing and extended here, is the easiest explanation because it makes a good continuation. Law of closure, elements which are not directly perceived are experienced in order to complete a figure, like Nessie here. Symmetry and parallelism are important laws. So here you see symmetry. It's like this famous vase with two faces, that you have always two lines forming a symmetrical pair. And parallelism, here you have two lines which have a constant distance from each other. Figure background segregation, distinguishing an object from its surrounding, might also play a role, where you see here the black figure, like a seahorse, and this might switch what you actually bind to the figure and what you bind to the background. You see already, this is a list, and if I ask you, is it a complete list? Hard to tell, which is a problem already, because we would like to have a strict algorithm to say, okay, now is it a good gestalt or isn't it? Indeed, there have been new laws found. So synchrony, items that change together. So here, the repeated rows should indicate changes over time. So you see a black dot blinking, white, black, and so on, and other dots in a different rhythm. And you bind those together, who, so to say, blink together. Common regions, objects in the same closed regions, are perceived in conjunction. So please note that actually these two circles are closer to each other than these two. Yet the binding due to the closure is very strong. Nobody would say these two belong together to one object, obviously. And element connectedness equally overcomes proximity. This is a problem. How can we clearly determine the best and the most stable form, and what would be an experimental procedure? So if I show you a new stimulus, and I give you the parameters, I would like to have an algorithm where I put in the distance between elements, the relative motion vector, different stuff which I can compute, and I get a result, and the result is, well, it's bound to a figure or not, or gives me a unique answer. And this is obviously a problem here. I've shown you in quick succession roughly 10 different Gestalt laws, and they have this subjective feel. And this led to the attitude that the work of Gestalt psychology is largely descriptive and does not really solve problems. And therefore, after the 1920s or so, it fell a little bit out of regard and was neglected, and only nowadays, when we can do a probabilistic formulation of the same concepts. So imagine what is the chance that two objects which are formed this way and are independent of each other give, from your viewpoint, exactly this visual impression. They must be perfectly aligned. And as soon as you have a reasonably flat prior of the relative position, the probability of such a visual stimulus arising out of two objects opposing each other, like shown here to the right, is extremely low. So the idea nowadays is that we can explain the Gestalt laws based actually on the statistics of natural stimuli. What is seen often and what is occurring rarely. And we just naturally choose the most plausible, most probable solution. So it's early for the interlude and the video, but well, you get it now. Wait a moment.
Of all the things we need to recognize, there's one which is fundamental to how we live our lives: the human face. It's how we know who someone is, whom we love, whom we hate, and whom we fear. Our brains seem tuned to spot faces.
We have so much hardware in our heads that is dedicated to recognizing faces. It takes almost nothing to make us see a face. I mean, just a big chunk of our brain is saying, where's the face? Where's the face? So, you know, the most minimal configuration of lines and a couple of curves will look like a face. Even, you know, clouds, the man in the moon, just, you know, the pattern of craters on the moon, we see as a face.
But Lincoln Holmes finds recognizing a face impossible. 30 years ago, he was in a car accident that damaged an isolated part of his brain, and he is now completely face blind.
On those moments when I am suddenly alone and I don't know where anybody that I'm with is, there can be a surge of fear, and it's lonely in that sense. The very thought of something so basic as recognizing faces being lost is not only hard to imagine, but it's pretty scary. One of the things that makes it hard for people to believe that I have such a deficit is that I'm not blind. I see them. And seeing in our vocabulary is synonymous in some ways with understanding. I see what you mean. And it's very hard for folks to understand that I can see them and not know who they are.
Sometimes it seems like maybe he recognizes me because I'm in the right place at the right time. I've said we're going to meet at such and such a location, and he finds me and he says, "Hi, Holly." But I think it's because we've made pre-arrangements that, yes, we're going to meet at X place at X time.
Maybe another way to put that is that when there are just the two of us sitting here, that's one thing. When we go to the supermarket, say, and get separated, then there are a couple of dozen female faces walking all around. I haven't got a prayer.
Right.
I haven't got a prayer.
Right.
I haven't got a prayer picking you out of all those faces.
What's that?
That's a key.
Great.
That's an apple.
Okay.
That's a place setting with a knife, fork, and spoon and a plate.
All right. Who is it?
I don't know. I don't know.
Okay. Young woman, old woman?
To be very honest, I'm having trouble answering that question.
Well, let me give you some biographical details. She's a movie star from the 1950s, very glamorous. She sang Happy Birthday to President Kennedy once.
Marilyn Monroe?
Yes.
Marilyn Monroe, as you know, had a close affiliation with more than one Kennedy. But that's neither here nor there. When I'm asked by people sometimes, do faces just all look the same? The answer to that question is that no, they don't all look the same. And they say, well, why don't you recognize them? And the answer is, they don't all look the same, but they don't all, in other words, they don't all look like John Smith. None of them look like anyone. They all are faces, but they are not recognizable as anyone's face. Any of them.
He sees the skin, he can see the texture of the skin, he can see the individual features fairly well. But what he doesn't see is the totality of the face. He can't simultaneously apprehend all of those different parts together. And that's what we have to do to be able to recognize a face.
It's hard to imagine what Lincoln is actually seeing when he looks at a face. It seems that his brain is not allowing him to put all the pieces of the puzzle together. Instead, he is confronted with a jumbled up mixture of features which he cannot connect with even the most familiar of faces.
Okay, how about that person?
Don't know.
Any sense of familiarity?
No.
No. What about the, there's a child's face sort of looking over his shoulder. Any familiarity there?
This is the nastiest one of all, isn't it?
Yes.
This is me.
Yes. How do you feel looking at a picture of your own face and not recognizing it?
For me, it is a face. It's not my face. It's a face. And there is some sense of incompleteness there. But so be it.
Lincoln's story has helped reveal how our brains process faces. Each time we look at another human being, a specific facial recognition system is activated. It turns out that this system is so specialized, it only deals with faces which are the right way up. It seems that facial recognition is such a demanding and important part of our lives that we need to dedicate a whole subsystem of the brain to this task. And the work with Lincoln suggests that this face area plays no role in recognizing any other type of object.
Muhammad Ali, Cassius Clay.
Yeah, absolutely right. Good.
Albert Einstein.
Good.
It's oblong. It's got lots of legs on it. There's a black thing at the top of it. Don't know what it is.
If I told you that it was a kind of scrubbing brush, and what you refer to as the legs are actually the bristles.
Oh, okay.
The black part at the top is actually just a shadow that's falling from the lighting. It's not actually part of the object itself.
Okay, I can see how that would be a scrubbing brush.
Okay.
But I didn't get it.
Uh-huh.
In Ottawa, Kevin Chappell provides another vital clue to the brain's visual recognition system. He has no trouble with faces, but a car accident has left him totally unable to make sense of the world. He sees all the details, but not what things are.
Well, after all these years, I've kind of got used to it now. It's me, it's how I am, it's my world. Often I'll let things just pass me by. If I have to, then I'll make an effort to figure out what it is. For example, you know, the upper part of what I'm seeing is blue, therefore probably sky. The green is obviously, if it's sticking up, it creates the skyline. It's there are trees. If it's flat, it's you know, grass. That's how I make my sort of judgments about where I am. Many times I'm wrong.
It's a very interesting and fairly rare condition whereby the eyes are working just fine and can take in the light from the visual world in a perfectly normal fashion. The problem is, in Kevin's case, in being able to decode these signals and produce a coherent interpretation of the world. So it's not like he has lost his knowledge of what objects are, and it's not like he simply cannot produce the name for it. You know, maybe he's just forgotten what the word is. None of those can account for his problem. The problem is an inability for the information from the visual world that's coming into his brain to make contact with this knowledge that he has about objects.
I really don't know what the coloured squares. There are faces in the squares. I can see 7 faces.
What about in the parts where there aren't faces?
There are just red blotches and black blotches. Oh, they could be playing cards. The blotches is like.
So it's interesting that you were so rapidly able to pick up the faces, but the suits somehow didn't quite make sense to you.
So this was one of the longer videos, but it makes a very important point. It shows that processing in the brain is distributed and that binding or integrating information is essential. It's making that point on several levels. Yes, please. Yes, it's correct. So he would realize that he is standing in front of a mirror, but similarly, He said it's not his face,